Welcome to Boring Planet, where the universe is not treated as a spectacle that needs to perform, but as it truly is, vast, patient, and deeply unconcerned with speed. The universe does not rush, not because it cannot, but because nothing within it requires urgency to exist. From the moment space first began to stretch, long before there were stars to light it or atoms to fill it, change unfolded in a way that favoured slowness. Expansion did not arrive like an explosion tearing outward, but like a quiet adjustment, a gradual widening that continues even now, measured not in seconds or centuries, but in billions of years. When astronomers say the universe is expanding, they mean that the space between galaxies is increasing by amounts so small they are meaningless on human scales, distances growing by fractions that no sense, no instinct, no daily experience could ever detect. Even the most sensitive instruments must observe patiently, comparing light that has travelled for eons, searching for differences so subtle they hide inside noise. There is no moment when space announces it has grown, no tremor, no sound, no visible shift. Reality simply becomes slightly larger than it was before, and everything within it adjusts without protest. On the timescale of a human life, this feels indistinguishable from nothing happening at all. Years pass, generations replace one another, cities are built, eroded, rebuilt. Entire cultures rise, flourish, and disappear. Through all of it, the night sky seems unchanged, stars holding their positions, familiar patterns returning again and again. Yet this sense of permanence is an illusion created by short attention spans. Given enough time, those same stars drift, those same patterns unravel, and entire galaxies move into arrangements no one alive today will ever see. The universe is patient in a way that makes human impatience feel almost irrelevant. Stars embody this patience perfectly. They do not ignite suddenly. Clouds of gas and dust take millions of years to collapse under gravity before fusion begins. Once it does, a star enters a long period of balance, shining steadily as hydrogen is converted into helium at a controlled, unhurried pace. A star like the Sun will do this for around 10 billion years, its brightness changing so slowly that thousands of generations could live and die without ever noticing a difference. There is no race to burn fuel, no pressure to complete the process. Smaller stars take this even further, burning so slowly that they will outlive the current age of the universe many times over. Some of the oldest stars formed when the universe was still young, and they remain today, quietly shining with almost no change, carrying the chemical simplicity of an earlier cosmos. When stars do end, the moment may appear sudden, but it is only the final step of a process that began millions of years earlier. Even the most dramatic stellar deaths are part of a long preparation, not a rushed conclusion. Galaxies behave the same way. They're not static islands of light, nor are they chaotic swarms. They assemble gradually, drawing in gas, absorbing smaller companions, reshaping themselves through gravity over immense spans of time. When galaxies merge, the event unfolds over hundreds of millions or billions of years. Their outer regions overlap first. Stars slowly adjust their orbits. Long streams of light are pulled outward and then fade, and eventually two systems become one. Individual stars almost never collide. The distances between them are too vast. What looks violent in images is, in reality, a slow rearrangement guided by gravity's steady hand. Even the most extreme phenomena in the universe reflect this calm when viewed at the right scale. A supernova seems instantaneous when captured in a single frame, but it is the outcome of processes that began deep inside a star long before. A black hole merger releases enormous energy, yet the ripples it sends through space-time spread outward, thinning as they travel, arriving across the cosmos as disturbances so faint they are almost indistinguishable from the background of reality. Nothing cosmic ever needs to rush, because nothing cosmic is running out of time. Time itself is part of the system, stretching and bending with space, shaped by mass and motion, flowing differently in different regions but never breaking into chaos. Near massive objects, time slows. In emptier regions, it moves more quickly, but everywhere it remains smooth and continuous, a quiet sequence of cause and effect unfolding without pressure. From this perspective, the idea of being late loses meaning. There is no cosmic deadline, no expectation that something must happen by a certain moment. The universe allows events to occur when conditions permit, not before and not after. Structure forms where gravity gathers matter. Light appears where nuclear reactions ignite. Complexity emerges where stability lasts long enough to support it. This slowness is not inefficiency. It is what makes everything else possible. Because change happens gradually, structures endure. Because energy spreads slowly, patterns can form. Because nothing is forced to happen all at once, the universe can build layer upon layer of history without tearing itself apart. Every atom in your body is part of this long timeline, forged in stars that lived and died long before Earth existed, drifting through space for millions of years, becoming part of new systems before eventually arriving here. There was no rush in that journey. The universe did not hurry those particles along. They arrived when gravity and chemistry allowed them to, and not a moment sooner. And even now, as everything continues to move, that same unhurried rhythm quietly carries the story forward. The slowness that shapes the universe does not mean stillness, and in fact almost nothing is ever at rest. Motion is everywhere, layered and continuous, yet so evenly shared that it leaves no trace in sensation. Earth feels solid beneath your feet not because it is still, but because everything on it is moving together. The planet turns steadily on its axis, completing a full rotation every 24 hours, a movement so consistent that it has defined the rhythm of days for billions of years. At the equator, the surface travels at more than 1,600 kilometers per hour, faster than most aircraft, yet there is no feeling of speed. No wind rushes past, no force presses against the body. Gravity binds the ground, the oceans, the atmosphere, and everything living on the surface into a single system, all sharing the same motion, all carried together. This is why movement can feel like rest when it is smooth and uninterrupted. Earth's rotation is only one layer of a much larger journey. At the same time it spins, the planet follows a curved path around the Sun, completing one orbit each year. This motion is not circular, but slightly stretched, a gentle ellipse shaped by gravity and momentum. The distance between Earth and the Sun changes gradually over the course of the year, enough to influence climate and seasons, but never enough to threaten stability. The orbit is self-correcting, balanced by forces that have remained reliable for billions of years. Earth does not need to be guided along this path moment by moment. Once set in motion, it continues naturally, following the curvature of space around the Sun, falling forward endlessly without ever colliding. Again, this movement leaves no physical sensation. There is no feeling of falling through space, no awareness of speed. The laws of motion allow constant velocity to feel exactly like standing still, and so an entire planet can race through space while its surface remains calm. The Sun itself is not a stationary anchor. It carries Earth and the rest of the solar system along as it orbits the center of the Milky Way. This orbit is immense, a slow procession through the galaxy that takes around 230 million years to complete. Since the Sun formed, it has completed only a small number of these galactic circuits. Every chapter of human history, every fossil record, every trace of civilization exists within a tiny fraction of a single orbit around the galactic center. The speed is enormous by everyday standards, roughly 200 kilometers per second, yet once again, there is no sensation of the movement. The solar system glides through the galaxy without friction, without sound, without resistance. One star among hundreds of billions, all tracing their own paths through a shared gravitational landscape. The Milky Way is not a rigid structure either. It rotates, its stars moving at different speeds depending on their distance from the center, its spiral arms forming, patterns that persist not because they are fixed objects, but because they are regions where matter tends to gather. Stars enter and leave these arms over time, like cars moving through slow traffic waves on a highway. Nothing abrupt happens. The motion is collective, gradual, and endlessly repeating. Beyond the Milky Way, motion continues on even larger scales. Our galaxy is part of a small association known as the Local Group, a loose collection of galaxies bound together by gravity across millions of light years. The Milky Way and the Andromeda Galaxy dominate this group, accompanied by dozens of smaller galaxies that orbit, drift, and interact in slow, complex ways. These galaxies are not fixed in place. They move toward one another for vast spans of time, their paths shaped by mutual attraction and the influence of unseen mass. The approach of Andromeda toward the Milky Way is measured in tiny increments, a few hundred kilometers per second across a distance of more than 2 million light years. On human timescales, this motion is meaningless. Entire civilizations could rise and vanish without the gap between the two galaxies appearing to change at all. Yet given enough time, the motion becomes inevitable. Billions of years from now, the two galaxies will begin to merge, not as a collision in the usual sense, but as a slow interweaving of stars, gas, and dark matter. Even now their outer halos overlap, long before their bright disks ever meet. The Local Group itself is not isolated. It drifts through space along with larger structures, pulled subtly by the gravity of neighboring galaxy groups and clusters. This motion is not directed toward a single destination, but shaped by the distribution of mass across enormous distances. Galaxies follow gradients in gravity the way rivers follow gradients in land, moving from regions of a lower density toward regions of higher concentration. This motion, too, is slow and smooth, unfolding over hundreds of millions of years. There is no sense of acceleration that could be felt from within. Everything moves because gravity allows it to, and everything moves together. What makes all of this possible is the way motion is shared. When everything in a system travels at the same speed in the same direction, there is no internal reference point that can register that movement. The atmosphere moves with Earth. Earth moves with the Sun moves with the galaxy moves with its neighbours. At every level, motion is layered but coordinated, smoothing itself into a background condition rather than an experience. This is why the universe can be so active and yet feel so calm. Motion does not have to be loud. It does not have to be dramatic. It can be continuous, predictable, and gentle enough to disappear entirely from awareness. Even the light reaching your eyes carries evidence of this constant movement. Photons leave the surface of the Sun and travel through space for more than 8 minutes, before arriving at Earth, crossing a distance that itself is changing as space slowly stretches. light from distant stars and galaxies travels for millions or billions of years, passing through regions that are themselves in motion, shaped by gravity and expansion. By the time that light arrives, the source may have moved, changed, or disappeared entirely. Yet the light carries no sign of haste. It arrives at the same speed regardless of the motion of its source or destination, indifferent to the long journey it has taken. In a universe defined by motion without disturbance, movement does not announce itself. It simply happens, quietly and continuously, shaping everything while asking nothing in return. The sky often feels like the most stable thing we know, a backdrop that returns unchanged night after night. But nearly everything in it is already ancient by the time we see it, shaped by processes so slow they hide behind familiarity. The moon is a perfect example. It looks fixed in its place, tracing the same path across the sky, cycling through phases that feel timeless, yet it is quietly moving away from Earth. Every year, the moon drifts about 3.5 centimeters farther from us, a distance roughly equal to the growth of fingernails over the same time. This motion is so small it escapes notice, but it has been happening for billions of years. When the moon first formed, likely from debris left after a collision between Earth and a Mars-sized body, it was much closer. Back then, it loomed large in the sky, tides were stronger, and Earth's days were far shorter. The slow recession of the moon is the result of an exchange of energy between Earth and its companion, a quiet transfer that unfolds through the movement of oceans. As the moon's gravity pulls on Earth, it raises tides, bulges in the oceans that do not align perfectly beneath it, because Earth is rotating. These bulges are carried slightly ahead, and as the moon pulls back on them, it steals a tiny bit of Earth's rotational energy. That energy moves the moon into a slightly higher orbit, while Earth's rotation slows by an almost immeasurable amount. This process continues without interruption, a steady handoff of motion that lengthens days by milliseconds over millions of years. The tides are not just water moving back and forth, they are a record of deep time, a physical connection between Earth and the moon that has been shaping both bodies since their earliest history. Even the moon's surface tells this story. Its face is marked by craters that have not been erased because there is no atmosphere to wear them away, no weather to soften their edges. Each impact remains as it was, left, a fossil of collision events that mostly happened billions of years ago, when the solar system was young and crowded. Looking at the moon is not just seeing a nearby object, but seeing a preserved archive of early solar system history hanging quietly above us. The sun, too, appears immediate and present, rising each morning as if on schedule, yet even its light is already old when it reaches us. Sunlight takes a little over 8 minutes to travel from the surface of the sun to Earth. The photons that warm your skin and illuminate the day began their journey before you noticed them, crossing nearly 150 million kilometers of space. During those 8 minutes, Earth continues to rotate, the planet moves along its orbit, and space itself stretches imperceptibly. What arrives feels instantaneous only because the delay is small compared to human attention spans. But on a cosmic scale, even this nearby light is delayed information, a message sent across space that arrives slightly after it was created. The sun itself is far older than any human structure, having formed about 4.5 billion years ago from the collapse of a cloud of gas enriched by earlier generations of stars. Its steady output of light is the result of a delicate balance maintained over immense time, hydrogen fusing into helium at its core in a process that has barely changed since life first appeared on Earth. Each ray of sunlight carries not only energy, but history, evidence of conditions deep inside a star that has been shining for billions of years without pause. The stars beyond the sun push this sense of delayed presence even further. The light from the nearest star system takes more than 4 years to reach us. Light from many of the stars visible in the night sky began its journey before modern civilization existed. Some of it left its source when humans were still painting on cave walls, and some when our species had not yet evolved at all. When you look up, you're not seeing the sky as it is now, but as it was across a wide range of past moments, layered together into a single view. This does not make the sky deceptive. It makes it historical. Every familiar point of light is a memory, carried across space with unwavering consistency. Even the colours of the sky are shaped by time and distance. The blue of daylight comes from sunlight scattering in Earth's atmosphere, a thin shell of gas that exists only because gravity has held it in place for billions of years. Without that long-term stability, there would be no air to scatter light, no sky to colour, no gradual blending of day into night. The calm reliability of the sky is the result of countless slow processes aligning just well enough to persist. The sun's position in the galaxy, the Earth's orbit, the moon's stabilizing influence on Earth's tilt, all of these factors work together across deep time to create something that feels simple and familiar, yet none of it is accidental or recent. Even the patterns we recognize as constellations are temporary arrangements. Stars that appear close together are often separated by vast distances, moving independently through space. Over tens of thousands of years, these patterns shift and dissolve, reshaping the sky into forms no human has ever named. The fact that they appear stable at all is a coincidence of timing, a brief overlap between slow stellar motion and short human lives. To look at the familiar sky is to look at a collection of ancient processes paused only by perspective. The moon, the tides, the sunlight, the stars, all of them are part of long, quiet stories that began billions of years ago and continue without interruption. Familiarity does not make them simple. It just makes their age easier to overlook. By the time motion begins to feel ordinary, it becomes easy to imagine space as a kind of empty stage where events happen, a passive backdrop against which planets move, stars shine, and galaxies drift. But space is not a container that simply holds the universe. It is part of the universe itself, inseparable from time, shaped by everything that exists within it. The idea that space and time are woven together into a single fabric did not come from imagination, but from careful observation, from noticing that motion, gravity, and the passage of time are deeply connected. When objects move, when mass gathers, when light travels, space and time respond together, bending and stretching in ways that guide what happens next. Gravity, in this view, is not a force pulling things through space like an invisible rope. It is the shape of space itself, curved by the presence of mass and energy. A planet does not orbit a star because it is being constantly pulled inward. It follows a curved path, because the space around the star is shaped in such a way that straight motion naturally becomes circular. The planet is moving forward, always forward, but the geometry of space bends that forward motion into a loop. This is why motion in the universe often feels effortless. Objects are not fighting against forces to stay in motion. They are simply following the paths that space allows. Once this idea settles in, many familiar motions take on a different character. Earth does not need continuous effort to circle the sun. It is already moving through curved space, and that curvature defines its path. The moon does not cling to Earth through some invisible tension. It travels along a route shaped by the combined curvature created by both bodies. Even light, which seems to move in perfectly straight lines, will curve when it passes near massive objects, not because it is being pulled, but because the space it travels through is not flat. This bending of light is subtle near small masses, but dramatic near dense regions like galaxy clusters, where entire arcs and rings of distorted light can appear, revealing the hidden shape of space itself. Time is woven into this structure as well. The passage of time is not the same everywhere, because time responds to gravity just as space does. Near massive objects, where space is more strongly curved, time moves more slowly. Far from mass, in emptier regions, time flows more quickly. This is not a philosophical idea or a metaphor. It is something that can be measured. Atomic clocks placed at different heights on Earth tick at slightly different rates. Satellites in orbit experience time differently than clocks on the ground, and their systems must correct for this difference to function properly. Time is not a universal river flowing at the same speed everywhere. It is part of the landscape, shaped by mass and motion, changing subtly from place to place. This means that nothing in the universe moves independently of its surroundings. Motion is always a response to geometry. Objects do not decide where to go. They follow the paths available to them, the natural routes defined by the structure of space-time. This is why motion can remain so stable over long periods. Orbits persist because the shape of space remains consistent. Systems endure because their geometry does not change quickly. When changes do occur, they ripple outward, altering paths gently rather than snapping them into new directions. Even dramatic events like the collapse of a massive star into a black hole are, at their core, geometric transformations. As matter collapses, it curves space more strongly, changing the behavior of time and the available paths for anything nearby. What we perceive as extreme gravity is, in this framework, an extreme shaping of space-time, where the usual distinctions between space and time begin to blur. Paths that once allowed escape no longer do. Directions that once pointed outward now lead inevitably inward. Yet even here, nothing is acting with intent or force. Space has simply taken on a new shape, and everything responds accordingly. On the larger scales, this shaping of space guides the structure of the universe itself. Galaxies form where space-time curvature encourages matter to gather. Filaments stretch across vast distances because the underlying geometry allows matter to flow along them. Voids exist where curvature is minimal, where matter has little reason to linger. The universe's structure is not imposed from the outside. It emerges naturally from the way space and time respond to mass and energy over long periods. This is why earlier ideas of space as an empty container fall short. Space is active. It participates. It carries information, responds to change, and influences outcomes. When space-time ripples, as it does when massive objects collide, those ripples carry energy across the universe, altering distances by tiny amounts as they pass. These gravitational waves are not objects moving through space. They are changes in space itself, travelling outward like a quiet adjustment propagating through the fabric of reality. Motion, then, is not something layered on top of the universe. It is built into the universe's structure. Nothing moves through space as if space were separate. Everything moves because of space, guided by its shape, responding to its curves, unfolding along paths that have been there all along. This perspective brings a certain calm to the way we understand cosmic motion. There is no constant struggle, no need for force to be applied moment by moment. Once a system is set in motion, it continues naturally, carried by geometry rather than effort. The universe does not need to push things around. It only needs to exist in a particular shape, and everything else follows. Long after motion, structure, and shape settled into the patterns we recognize, the universe kept a memory of its earliest moment of calm, and that memory still exists everywhere at once. In the beginning, the universe was not transparent. It was hot, dense, and filled with a glowing fog of charged particles. Light existed, but it could not travel freely. Photons were constantly scattered by free electrons bouncing endlessly, trapped in a bright, opaque sea. Space was smaller then, matter was closer together, and temperature ruled everything. For hundreds of thousands of years after the universe began expanding, there were no stars, no planets, no galaxies, and no darkness. There was only this uniform glow, a universe lit from within, but impossible to see through. As expansion continued, space slowly stretched and cooled. Temperature dropped not suddenly but steadily, until a quiet threshold was crossed. Electrons lost enough energy to settle into stable orbits around nuclei, forming the first neutral atoms. This moment is called recombination, not because things came together for the first time, but because particles that had been separated by heat were finally allowed to stay together. When that happened, the fog cleared. Light, suddenly unimpeded, was released in every direction at once. Those photons began a journey that has never stopped. They spread outward as space expanded, their wavelength stretching along with it, their energy thinning gently over billions of years. What was once brilliant visible light slowly cooled into infrared, then into microwaves, until it became a faint uniform glow filling all of space. This glow is known as the cosmic microwave background, and it is the oldest light we can observe. It does not come from stars or galaxies. It comes from the universe itself, from the moment it first became transparent. It surrounds us completely, arriving equally from every direction, not because we are at the center of anything, but because that light was released everywhere at once. No matter where you are in the universe, this background would still be there, the same soft afterimage of early clarity. The cosmic microwave background is remarkably uniform, almost the same temperature in every direction, about 2.7 degrees above absolute zero. This temperature is not arbitrary. It is the cooled remnant of a universe that was once thousands of degrees hot. The fact that it is so even tells a story of balance and patience, of expansion that smoothed out extremes over immense time. Yet it is not perfectly uniform. Tiny variations exist, differences of only a few millionths of a degree frozen into the light itself. These slight irregularities are not noise, they are the seeds of everything that followed. Regions that were just a little denser than average would eventually gather more matter, becoming the first stars and galaxies. Regions that were slightly emptier would become cosmic voids. The entire large-scale structure of the universe can be traced back to these minute variations, preserved in the background glow like ripples in cooling glass. Even now, as galaxies form and evolve, as stars ignite and fade, this ancient light continues to pass through everything. It does not fade away in the usual sense. As space expands, its wavelength stretches, but it remains present, a constant thermal backdrop to all of cosmic history. The universe, in this way, has a temperature, not because it is heated by stars, but because it remembers being hot. That memory is unavoidable. Even the emptiest regions of space, far from any galaxy, still sit at this background temperature, bathed in ancient radiation. There is no place colder than this, because there is no place untouched by the early universe. The cosmic microwave background is not something you can see with your eyes, but it is not abstract. Radios and detectors can pick it up as a faint hiss, a background signal that exists even when all other sources are removed. In a very real sense, part of what we call static is the universe speaking softly about its past. This background acts as a kind of anchor, a reference point that does not change quickly, if at all. Stars come and go. Galaxies collide and merge. Space continues to expand. But this glow remains, cooling only as fast as the universe allows, changing so slowly that it feels eternal. It ties every moment of cosmic history back to the same origin, reminding us that everything complicated and structured emerged from something once simple and smooth. The clarity of that early moment never vanished. It thinned, stretched, and softened, but it stayed. The universe does not erase its beginnings. It carries them forward, woven quietly into the background of everything that exists, still surrounding us, still present, still telling the same ancient story without urgency or insistence. By the time light had spread freely and space had settled into its long expansion, another influence was already at work, one that would quietly determine how the universe arranged itself on the largest scales. When astronomers first began to measure how galaxies rotate, they expected a simple pattern. Stars closer to a galaxy's center should orbit more quickly, while stars farther out should move more slowly, just as planets in the solar system do. Gravity from the visible mass should weaken with distance and orbital speeds should drop. But that is not what the universe does. Instead, stars far from galactic centers move at nearly the same speed as those much closer in. Galaxies spin as if they are embedded in far more mass than we can see, mass that does not shine, does not absorb light, and does not reveal itself directly. If only the visible stars and gas were present, galaxies would not remain intact. They would slowly unravel, stars drifting away into space. The fact that they do not tells us that something else is there, something holding everything together quietly and persistently. This unseen influence is called dark matter, not because it is sinister or mysterious by nature, but because it does not interact with light in any way we know how to detect directly. It does not glow, reflect, or block light. It does not clump into stars or planets, yet it has mass and it responds to gravity. Wherever galaxies form, dark matter appears to be present first, gathering into vast invisible halos that extend far beyond the visible edges of galaxies. These halos provide the gravitational framework within which stars and gas settle. Without them, galaxies as we know them would not exist. The visible parts of a galaxy are only the brightest trace of a much larger structure, like frost outlining an unseen surface. The idea of dark matter did not emerge from a single observation, but from a pattern that repeated across the universe. Galaxy after galaxy showed the same unexpected rotation curves. Clusters of galaxies behaved as if they contained far more mass than their visible content suggested. Light from distant galaxies bent as it passed through space in ways that could not be explained by luminous matter alone. This bending, known as gravitational lensing, reveals mass through its effect on space-time, regardless of whether that mass emits light. Again and again, the same conclusion appeared. Most of the matter shaping the universe is invisible. Dark matter does not form familiar structures. It does not make clouds, stars, or solid objects. It passes through ordinary matter almost without interaction, streaming through galaxies and even through bodies without leaving a trace. Earth moves through a halo of dark matter as it orbits the Sun. and trillions of dark matter particles likely pass through every square centimetre each second, unnoticed and unchanged. This does not make dark matter ghostly or ethereal. It simply means it plays by different rules than the matter we're used to. Its presence is felt only through gravity, and gravity works patiently. Over long periods, dark matter gathers, not into dense clumps, but into broad, diffuse structures. These structures formed early, when the universe was still young, providing the scaffolding on which everything else would later assemble. Gas fell into these gravitational wells, cooled, and eventually formed the first stars and galaxies. In this sense, dark matter set the stage long before the visible universe took shape. It does not drive change quickly or dramatically. It holds things in place, allowing slow processes to unfold without disruption. The calm persistence of galaxies owes much to this unseen mass. Without it, stars would move too quickly, orbits would be unstable, and the gentle, long-lived structures we observe would not survive. Dark matter smooths motion, deepens gravitational wells, and creates environments where systems can remain intact for billions of years. Even galaxy clusters, the largest bound structures in the universe, rely on dark matter to maintain coherence. The hot gas between galaxies in these clusters would escape if visible matter were all that existed. Instead, it remains trapped, glowing faintly in X-rays, held by gravity from something we cannot see. On the larger scales, dark matter shapes the cosmic web itself. Vast filaments stretch across hundreds of millions of light years, connecting clusters of galaxies, while enormous voids remain nearly empty. These patterns reflect the distribution of dark matter, which gathered into filaments under gravity long before stars ignited. Galaxies formed along these filaments like condensation along invisible threads. What we see in the night sky is only the illuminated portion of a much larger, darker structure. Dark matter does not hurry. It does not collide, radiate, or decay in ways that would announce its presence. It simply exists, shaping space through gravity, providing stability through mass, and allowing the universe to build complexity slowly and reliably. In a universe where nothing rushes, dark matter is the quietest participant of all, doing most of the structural work without ever asking to be noticed. It does not seek attention, but without it, the universe would be far less calm, far less ordered, and far less capable of sustaining the long stories that stars, galaxies, and light continue to tell. As dark matter gathered quietly and light began to trace its outlines, the universe started to reveal a shape that only becomes visible when viewed across immense distances. Individual stars and galaxies tell local stories, but when astronomers step back far enough, patterns emerge that are not random and not imposed, but grown. Matter does not scatter evenly through space. It follows preferences dictated by gravity, settling into an architecture that looks less like a cloud and more like a network. This structure is known as the cosmic web, and it stretches across the observable universe, connecting everything that has mass into a vast, delicate framework. The cosmic web did not appear fully formed. It emerged slowly, seeded by the tiny density differences preserved in the oldest light. Where the early universe was just slightly denser, gravity worked a little more effectively, pulling matter inward over time. These small advantages compounded over billions of years as regions with slightly more mass attracted more matter, growing gradually into filaments. Between these filaments, matter thinned out, leaving behind enormous voids where very little remains. This process did not require direction or design. It followed the simplest rule gravity offers: matter flows toward matter. Given enough time, this rule creates complexity without effort. Filaments are not thin lines in space. They're vast structures, hundreds of millions of light-years long, containing countless galaxies and immense amounts of dark matter. Along these filaments, galaxies form and evolve, drawn together by shared gravitational wells. At the intersections of filaments, where gravity is strongest, galaxy clusters take shape. Massive gatherings of hundreds or thousands of galaxies bound together across deep time. These clusters are some of the most stable structures in the universe, held in place by the combined gravity of visible matter and far larger quantities of dark matter. Between filaments lie voids, regions so empty they can span tens or even hundreds of millions of light-years, with only a handful of galaxies scattered inside. These voids are not failures of formation. They're a natural outcome of matter flowing away toward denser regions. Over time, as gravity pulls matter into filaments and clusters, the voids grow emptier, expanding gently as space itself expands. The universe, on its largest scales, resembles a foam or a sponge, with dense walls surrounding vast hollow spaces. This pattern is not something that can be seen all at once with the telescope. It emerges only when millions of galaxies are mapped and their positions compared. Surveys of the sky reveal that galaxies are not arranged randomly, but trace these enormous threads, outlining the invisible structure beneath them. The cosmic web is not static. It continues to evolve, but it does so slowly. Filaments thicken as more matter flows along them. Clusters grow by merging with smaller groups. Voids expand and become emptier. All of this happens on timescales so long that the overall pattern appears fixed, even though every part of it is in motion. Gravity does not rush the process. It allows matter to respond at its own pace, settling into configurations that minimize energy and maximize stability. There is a quiet efficiency to this organization. The universe does not attempt to fill space evenly. It allows imbalance, because imbalance creates structure. Regions of higher density become sites of complexity, while emptier regions remain calm and sparse. This contrast is what allows galaxies to form and persist without colliding constantly. Space is not overcrowded. It is carefully partitioned by gravity's slow influence. Even the largest structures known follow this rule. Superclusters, collections of galaxy clusters linked by filaments, stretch across hundreds of millions of light-years. Yet beyond them, space opens again into voids, preserving balance on even greater scales. The universe does not collapse inward, nor does it fragment into chaos. It finds a middle ground, a dynamic equilibrium shaped by expansion and attraction working together. Expansion stretches space, encouraging separation. Gravity pulls matter inward, encouraging connection. The cosmic web is the result of these two influences negotiating over billions of years. This architecture also explains why the universe looks different depending on scale. Up close, it appears rich and varied, full of stars, nebulae, and galaxies. From farther away, patterns emerge. From farther still, the universe becomes smooth again, the individual filaments blending into an overall uniformity. This transition from complexity to simplicity is another expression of patience. The universe allows detail where gravity has time to act, and uniformity where it has not. Nothing in the cosmic web was placed deliberately. There was no blueprint, yet the result is coherent and stable, a structure that supports galaxies without forcing them, that creates order without rigidity. Matter gathers the way it does because gravity prefers connection, and given enough time, those connections trace lines, surfaces, and networks that endure. The universe does not build quickly, but it builds well, layering structure upon structure until even emptiness has a shape. Between the filaments and clusters, beyond the places where matter chose to gather, lie regions so sparse they challenge intuition. These intergalactic voids are not small gaps or empty pockets tucked between busy systems. They are enormous expanses stretching tens or hundreds of millions of light years, where almost nothing happens. When astronomers map the universe on its larger scales, these voids dominate the volume. Most of the universe is not filled with stars, galaxies, or even gas. It is defined by absence, by regions where matter is so thinly spread that the idea of emptiness begins to take on physical meaning. Inside a typical void, galaxies are rare. You might travel millions of light years without encountering a single one. The few that do exist are often small, faint, and isolated, forming stars slowly, as if responding to an environment that offers little encouragement. The density of matter in these regions can be less than 1 atom per cubic meter, far emptier than even the best vacuums created on Earth. Yet this emptiness is not absolute. Even the most vacant regions still contain traces of gas, a whisper of particles drifting through expanding space, and the ever-present background of ancient light. Nothingness in the universe is never truly nothing. It is simply the lowest setting on a very wide scale. The temperature of these voids reflects this quiet state. Far from stars and galaxies, space cools toward the background temperature, set by the cosmic microwave background just a few degrees above absolute zero. There is no sunlight to warm it, no collisions to generate heat, no dense matter to retain energy. The cold is not sharp or biting. It is gentle, passive, a condition rather than an experience. Energy has spread thinly here, diluted by expansion and distance, leaving behind a calm thermal floor that changes only over immense time. These regions are not dramatic. There are no storms, no sudden events, no rapid transformations. Processes unfold so slowly that change becomes almost hypothetical. A stray atom might drift for millions of years without encountering another. A faint gravitational influence might nudge a particle's path by an imperceptible amount over eons. This is space at its most relaxed state, not striving towards structure, not collapsing inward, simply expanding along with the universe itself. The existence of voids is not an accident or a flaw. They are a natural consequence of gravity's preference. As matter flowed toward denser regions to form filaments and clusters, other regions were left behind, gradually emptied as material drained away. Over time, these voids grew larger and emptier, their boundaries defined by the surrounding cosmic web. Expansion plays a role as well, stretching these regions and further lowering their density. The universe does not try to fill its emptiness. It allows it to grow, to persist, to become a defining feature rather than a temporary gap. Even light behaves differently in these vast open spaces. With so little matter to interact with, photons travel almost entirely unimpeded, crossing voids without scattering or absorption. In a sense, voids are some of the clearest windows the universe offers, regions where space reveals its most transparent state. Yet because there is so little to see, they appear dark, not because they hide information, but because there is almost nothing there to emit it. This darkness is not threatening. It is simply the absence of activity. The scale of these voids has subtle effects on the universe's overall behavior. Light passing through them can experience tiny shifts due to differences in gravitational potential, a gentle stretching or compression that leaves faint imprints on observations. The distribution of voids influences how galaxies move, how clusters interact, and how the cosmic web evolves over time. Emptiness is not inert. It participates quietly, shaping paths by what it lacks as much as dents. Regions shape them by what they contain. When compared to the crowded environments of galaxies, voids feel like the universe at rest. They represent the outcome of all that patient motion and gathering, the places left untouched by complexity. In these regions, the universe approaches its simplest state, space expanding, energy diluted, matter sparse. This simplicity is not a beginning or an end. It is a stable condition that can persist for billions of years without interruption. Most of the universe exists in this state, not because it failed to form stars or galaxies, but because gravity naturally creates contrast. Where there are dense structures, there must be empty spaces between them. Together, they define the universe's balance. The calm of the voids offers a reminder that activity is not the default condition of reality. Stillness, or something very close to it, occupies most of existence. The universe is not loud or crowded everywhere. It allows vast regions to remain quiet, cold and thin, carrying on with almost nothing happening at all and finding no urgency in that emptiness. Even in a universe that prefers stability, not all stars shine in exactly the same way from one moment to the next. Some stars change, not because they are failing or ending, but because their internal balance moves through slow, repeatable cycles. These are variable stars, and their changes are among the most quietly reliable rhythms in the cosmos. From a distance, they appear to brighten and dim, sometimes over days, sometimes over months or years, following patterns that repeat with remarkable consistency. The variations are not random flickers or surface disturbances. They are the visible expression of processes unfolding deep inside the star, far beneath the glowing surface. Inside a star, energy produced in the core must travel outward before it can escape as light. This journey is not instantaneous. Photons can take thousands or even millions of years to move from the core to the surface, bouncing through dense plasma, transferring energy step by step. Along the way, pressure builds, layers expand, and gravity pulls back. In many stars, this balance settles into a steady state, producing a constant output. In others, the balance gently overshoots and corrects itself, leading to rhythmic expansion and contraction. When a star expands, its surface cools slightly and its brightness changes. When it contracts, it heats up again. The cycle repeats, driven by the physics of pressure, temperature, and gravity interacting over long time scales. These pulsations are not surface phenomena. They involve the entire star breathing in and out, sometimes by a few % of its radius, sometimes by much more. Certain types of variable stars, such as Cepheids, follow especially regular patterns. Their pulsation periods are so stable that they can be used as cosmic measuring tools. The time it takes a Cepheid to complete one cycle is directly related to its true brightness. By comparing how bright it appears from Earth to how bright it must actually be, astronomers can determine its distance with impressive accuracy. Entire maps of the universe have been built using these steady stellar pulses as reference points. A star changing its brightness becomes a ruler stretched across space. Other variable stars follow slower rhythms. Red giants, nearing later stages of their lives, can pulse over hundreds of days, their outer layers swelling and shrinking as internal processes adjust. These changes are not signs of collapse. They are part of a long transitional phase that can last millions of years. Even in these stages, the star is not rushing toward an end. It is moving through a sequence written by its mass and composition, unfolding step by step with no urgency. Some stars host internal waves, similar in concept to seismic waves on Earth. These waves ripple through stellar material, subtly altering surface motion and brightness. By observing these tiny variations, scientists can infer what is happening inside the star, mapping its internal structure without ever seeing beneath the surface. This field, known as astroseismology, treats stars as resonant objects, each with its own set of natural frequencies. A star's size, age, and internal layering determine how it rings. The universe, in this sense, is filled with stars that hum quietly, their vibrations too slow and deep for human hearing, but measurable through light. Not all variable stars are regular. Some change in complex ways, influenced by interactions with companion stars or shifts in internal energy transport. Binary systems can produce eclipsing variables, where one star passes in front of the other, dimming the combined light at predictable intervals. These changes are not due to the stars themselves altering, but to geometry, to motion along shared orbits. Again, the variation is orderly, governed by paths that repeat over long periods. What unites all these stars is that their change does not signal instability in the dramatic sense. They are not flickering because they are about to disappear. They are adjusting, redistributing energy, responding to conditions that evolve slowly over time. Their variability is part of how stars remain balanced, not how they lose control. The night sky, which can appear fixed and unchanging, is quietly full of these rhythms. Stars pulse, orbit, eclipse, and resonate, each following patterns shaped by physics rather than chance. Some of these stars have been pulsing the same way for millions of years and will continue to do so long after current civilizations are gone. Their cycles are patient, repetitive, and dependable, embedded within a universe that allows change without forcing conclusions. Stars do not all burn in silence. Some mark time, not with clocks, but with slow, luminous breaths, repeating their patterns again and again, not to announce an ending, but to maintain equilibrium across deep time. Not every planet spends its life circling a star. Some worlds move through the galaxy alone, detached from any sun, carrying no permanent source of light or warmth. These are rogue planets, and they are far more common than once imagined. Early models of planetary systems assumed that planets formed neatly and stayed where they belonged, but the reality turned out to be quieter and more chaotic. Planetary systems are shaped by gravity interacting over long periods, and gravity does not always settle gently. In the crowded early stages of a star system's life, young planets can tug on one another, exchanging energy, altering orbits, and sometimes pushing one of their own completely free. When that happens, a planet does not shatter or vanish. It simply continues moving, carrying the speed and direction it had at the moment of ejection, now set on a path that no longer loops back. A rogue planet becomes a traveller, drifting through interstellar space without attachment. Some rogue planets form this way, born around a star and later expelled. Others may form alone from collapsing clouds of gas that never grow large enough to ignite as stars. These objects blur the boundary between planets and failed stars, existing in a grey category defined more by mass than by origin. Regardless of how they form, once they are free, their lives change very little. With no star to orbit, there are no days or years, no predictable cycles of light and shadow. Motion continues, but reference points disappear. The planet travels through the galaxy along a quiet trajectory, influenced only by distant gravitational fields that alter its path gently over millions of years. the environment around a rogue planet is cold but not immediately frozen. Planets retain heat from their formation, energy locked into their interiors during collapse and differentiation. Massive rogue planets, especially those comparable in size to Jupiter, can glow faintly in infrared for billions of years, slowly radiating away their internal heat. Smaller rocky planets cool more quickly, but even they may retain warmth deep beneath their surfaces for long periods. Radioactive elements within their interiors continue to decay, providing a slow, steady source of energy. In this way, a rogue planet does not become inert the moment it leaves its star. It transitions into a long, gradual cooling phase, one that can last longer than the entire history of life on Earth. Some of these worlds may carry thick atmospheres, composed of gases trapped by gravity long before ejection. Without sunlight, atmospheres behave differently. Gases may freeze and settle onto the surface, forming layers of ice. On larger planets, pressure alone can keep atmospheres in a dense, stable state, even in deep space. Beneath ice layers, subsurface oceans could persist, warmed by internal heat rather than stellar radiation. These environments would be dark, insulated and remarkably stable, shielded from radiation and surface extremes. The idea that life could exist in such places is speculative, but not impossible. Life on Earth already thrives in deep oceans and underground, disconnected from sunlight, relying instead on chemical energy. Rogue planets offer the same ingredients in a more isolated form. Detection of these wandering worlds is difficult. Without a nearby star, they do not reflect light. Astronomers usually find them indirectly, through gravitational microlensing, brief events where a rogue planet passes in front of a distant star and bends its light just enough to be noticed. These detections suggest that rogue planets may be as numerous as stars in the galaxy, perhaps even more so. If that is true, then most planets in the Milky Way do not belong to solar systems at all. They exist alone, unseen, filling the space between stars with quiet mass. Despite their isolation, rogue planets are not truly disconnected from the universe. They move through the same galactic environment as stars and systems, passing through spiral arms, drifting through voids, occasionally passing near other stars without ever being captured. The distances between stars are so vast that close encounters are rare, and a rogue planet can wander for billions of years without approaching any system closely enough to matter. Its journey is long, uninterrupted, and largely uneventful. There are no dramatic moments, no sudden changes in direction, just steady motion through an environment that offers little resistance. This kind of existence highlights a different aspect of the universe's character. Not everything is organized into systems. Not everything revolves around a center. Some objects simply move, carrying their history with them, shaped by early interactions and then left to drift. Rogue planets are not failures or leftovers. They are natural outcomes of gravity working over time, evidence that the universe allows solitude as easily as structure. They remind us that belonging is not a requirement for persistence. A world can exist, cool, and endure without ever returning to a source of light. In the vastness between stars, these planets continue on, silent and unseen, holding on to their remaining warmth as the galaxy slowly turns around them. When gravity has nothing left to negotiate with, when mass has collapsed as far as the structure of space-time will allow, the result is not an object in the usual sense, but a region where gravity has completed its work. A black hole is often imagined as something violent or destructive, but that impression comes from thinking of it as a thing acting on its surroundings. In reality, a black hole is a place, a condition of space-time itself, defined not by what it does, but by what the geometry of space has become. Long before a black hole exists, its story begins quietly inside a massive star. For millions of years, the star balances outward pressure from nuclear fusion against the inward pull of gravity. When that fuel runs low, pressure weakens. Gravity, patient and relentless, begins to dominate. The core collapses inward, matter falling through itself, compressing beyond densities found anywhere else in the universe. If the remaining mass is great enough, no known force can stop the collapse. Space bends more sharply, time slows more deeply, and a boundary forms, not as a surface, but as a limit. This boundary is the event horizon. It is not a physical wall. It has no texture or thickness. It is simply the point beyond which paths that once led outward now lead only inward. From outside, nothing dramatic happens at the horizon itself. Space continues to curve. Time continues to flow. But beyond that boundary, all possible futures point toward the center. The event horizon marks the completion of gravity's influence, the place where escape is no longer part of space-time's shape. Approaching a black hole does not feel like falling toward a monster. From far away, it behaves like any other mass. A star or planet orbiting at a safe distance would notice nothing unusual. Gravity does not suddenly become stronger near a black hole than near any other object of the same mass. What changes is not the strength of gravity, but its geometry. Near the horizon, space-time curves so sharply that time itself begins to slow relative to distant observers. Clocks near a black hole tick more slowly than clocks far away. This effect is not theoretical. Time dilation has been measured near Earth, around satellites, and near dense stars. A black hole simply takes this familiar effect to its extreme. To an outside observer, an object falling toward the horizon appears to slow down, its light stretching and dimming, never quite crossing. To the falling object, time continues normally. There is no sudden moment of realization, no instant of destruction at the boundary. The horizon is not a place where something happens. It is a place where paths change character. Inside, space and time exchange roles in subtle ways. What once was a direction in space becomes as inevitable as time itself. Moving inward is no longer a choice, just as moving forward in time is not a choice outside. This is why a black hole is better understood as a region than an object. It is space-time configured so completely by gravity that no alternative futures remain. Even this completion is not chaotic. Black holes are surprisingly simple. Despite forming from complex stars, they are described by only a few properties: mass, spin, and charge. All the messy details of what fell in are smoothed away by gravity's final act. This simplicity is not destruction. It is compression, information encoded into geometry. On long timescales, black holes are not eternal traps. Quantum physics suggests they slowly radiate energy, a process known as Hawking radiation, so faint that it takes longer than the current age of the universe for a stellar mass black hole to noticeably change. Over unimaginable spans of time, even black holes may fade, returning their mass to space's diffuse energy. Again, there is no urgency. Even gravity's most complete expression unfolds patiently. Black holes do not rush to consume the universe. They sit quietly, shaping motion around them, deepening time, bending light, and marking the places where gravity finished what it started. They are not interruptions in the universe's calm, but confirmations of it. When mass collapses far enough, space-time adjusts, settles into a new shape, and continues on, unhurried, carrying that shape forward as part of the same long story. When massive objects move through the universe, they do more than change position, they alter the fabric that connects everything. Space-time is not rigid, and when enormous masses accelerate, especially when they orbit one another closely, the shape of space and time responds. These responses do not appear as light or heat or particles, but as waves, gentle distortions that travel outward at the speed of light. Gravitational waves are not carried by space-time, they are space-time, momentarily stretched and compressed as energy moves through it. For most of cosmic history, these waves passed unnoticed, not because they were rare, but because they are subtle, changing distances by amounts so small that they blend into the background of reality. The strongest sources of gravitational waves come from the most complete expressions of gravity. Pairs of black holes or neutron stars locked in slow spirals around one another. As they orbit, they lose energy, not through friction or light, but through the emission of these ripples. The orbit tightens gradually, the rhythm quickens, and over millions or billions of years, two objects become one. The final moments of a merger release an intense burst of gravitational waves, carrying information about the masses, spins, and paths of the objects involved. Yet even this intensity is relative. By the time these waves travel across vast distances and reach places like Earth, their effect is extraordinarily small. They do not shake planets or disrupt orbits. They gently stretch space in one direction, while compressing it in another, altering distances by less than the width of a proton across kilometers of space. When scientists first proposed the existence of gravitational waves, they understood that detecting them would be a challenge of patience and precision. Instruments would need to measure changes so small they would be drowned out by ordinary vibrations, thermal noise, and even the quantum motion of atoms. The eventual success came not from overpowering the signal, but from listening carefully enough. Large interferometers were built, using lasers sent down long, perpendicular tunnels. By comparing the time it takes light to travel back and forth along each path, these detectors can sense tiny differences in length. When a gravitational wave passes through, the distances change slightly, and the light's pattern shifts. Nothing moves violently. The detector does not jump or sway. It registers a whisper, a faint pattern that matches predictions made decades earlier. The first detection confirmed that space-time really does carry information, a signal that began more than 1 billion years ago, when two black holes merged in a distant galaxy, reached Earth and passed through quietly, unnoticed by everything except instruments designed to listen. The wave did not bring destruction or light. It brought shape, a momentary rearrangement of distances that revealed an event long past. Since then, dozens of such signals have been recorded, each one telling a story about massive objects meeting in the dark. These events are not rare. They happen constantly throughout the universe. What is rare is the ability to detect them. What makes gravitational waves especially calm in character is that they do not disrupt the universe they pass through. They do not accumulate or linger. They move outward, stretching and compressing space-time once, then leaving it as it was before. Even enormous collisions involving objects more massive than the Sun do not tear the universe or leave scars. They rearrange it briefly, then fade. The energy spreads thinly across space, diluted by distance, becoming part of the background of cosmic motion. In this way, even the most dramatic mergers respect the universe's preference for balance. Gravitational waves also offer a different way of knowing the universe. Unlike light, which can be blocked, absorbed, or scattered, these waves pass through matter almost unaffected. They carry information directly from regions that light cannot escape, such as the interiors of dense mergers or the immediate surroundings of black holes. This does not make them urgent or alarming, it makes them honest. They are records of motion written into space-time itself, arriving without distortion. Despite their importance, gravitational waves do not dominate the universe's behavior. They are one part of a much larger system, a quiet communication channel rather than a driving force. They confirm that space-time is dynamic, capable of carrying memory without holding on to it. After the wave passes, distances return to their usual values, and the universe continues as before, unhurried and intact. Even when gravity reaches its most extreme expressions, the result is not chaos, but a brief adjustment, a gentle ringing that fades back into silence. Light does not always take the shortest path, and in a universe where space itself can curve, a single beam can arrive more than once, carrying with it a quiet record of the journey it was forced to take. When light travels across the universe, it moves along the shape of space-time, not through an abstract emptiness. Massive objects bend space around them, and when light passes nearby, its path bends too, not because it is pulled like a particle, but because straight lines no longer point in the same direction they once did. This effect is known as gravitational lensing, and it transforms gravity into a kind of cosmic glass, reshaping what we see without altering the light itself. A distant galaxy may appear stretched into arcs, duplicated into multiple images, or even arranged into a perfect ring, not because it has changed, but because the space between it and us has taken on a new shape. These distortions are not errors or illusions. They are accurate maps of curvature, visual, evidence that space is doing exactly what mass requires it to do. In some cases, the alignment between a distant light source, an intervening mass, and the observer is so precise that light wraps fully around the foreground object, forming what is known as an Einstein ring. The light has not been scattered or broken. It has been guided along multiple paths that all lead to the same destination. Each path has a different length, a different geometry, and a different travel time. This means that the same event can arrive at different moments, spaced out across days, months, or even years. A single explosion, flare, or brightening in a distant galaxy may be seen more than once, not because it repeated, but because its light took different routes through curved space. In these delayed arrivals, the universe reveals a subtle form of memory. Light remembers the path it took, and by comparing these arrivals, astronomers can measure the shape of space itself. The delays are not arbitrary. They are determined by both distance and gravity, by how deeply space is curved and how long each route is. Even a difference of a few light days across billions of light years is enough to produce measurable delays. Nothing about this process is rushed. The lensing mass may be a galaxy cluster that has existed for billions of years, slowly shaping the paths of passing light without ever interacting with it directly. The background source may have long since changed or faded by the time its light finishes arriving along every path. What reaches us is a layered view of history, the same moment replayed gently, stretched out by geometry. Gravitational lensing also allows us to see things that would otherwise remain hidden. Distant galaxies that are too faint to detect on their own can be magnified by lensing, their light focused and amplified by curved space. This is not a boost in energy, but a redistribution of light across the sky, concentrating it where paths converge. In this way, massive structures act as natural telescopes, revealing regions of the universe that would be inaccessible even to the most powerful instruments. Again, This is not an active process. The lens does not choose what to show, it simply exists, and space responds. Light follows. Even dark matter, which cannot be seen directly, reveals itself through lensing. Because it bends space just like visible matter, its presence can be mapped by observing how background light is distorted. In this way, gravitational lensing becomes a quiet translator, converting invisible mass into visible patterns. The universe does not announce where its hidden matter lies. It allows light to trace the outline slowly, patiently, over millions of observations. In strong lensing systems, the same galaxy can appear as multiple images arranged symmetrically around a foreground mass. In weak lensing, the distortions are subtle, only detectable by averaging the shapes of thousands of galaxies. Both are expressions of the same principle: space curves. Light adapts, information arrives without urgency. The idea that light can arrive more than once challenges the assumption that observation is immediate. What we see is not always a single snapshot, but a composite, assembled by space-time itself. The universe does not deliver its messages all at once. It parcels them out along different routes, allowing time to stretch them into sequences rather than instants. Even when light takes the longest possible path, it does not hurry. It moves at the same constant speed, indifferent to distance, guided only by shape. In this way, gravitational lensing is not just a visual phenomenon, it is a reminder that space participates in storytelling. It edits, delays, duplicates, and magnifies, not to confuse, but to preserve. Light arrives carrying with it the imprint of every curve it followed, every mass it passed, every detour it was given. By the time it reaches us, it has already lived a long, quiet history, and sometimes it tells that history more than once. The Milky Way often gets spoken of as though it were a single object, a disk of stars rotating calmly in space. But that picture is only a simplification, a surface impression of something far more layered and historical. A galaxy is not a thing that exists all at once. It is a collection of structures that formed at different times, under different conditions, and were gradually assembled into a shared gravitational system. The bright band that stretches across the night sky marks only the densest, most obvious part, the disk, where stars, gas and dust are concentrated into spiral arms and ongoing star formation still occurs. This disk is thin compared to its width, rotating in an orderly way, its stars sharing roughly circular orbits around the galactic center. But even within this familiar component, age varies. Some stars in the disk are young and blue, born recently from collapsing clouds, while others are billions of years old, having completed many slow orbits since the galaxy was still forming. Above and below this disk lies the halo, a vast diffuse region extending far beyond what can be seen directly. The halo contains very little gas and almost no new star formation, but it holds some of the oldest stars in the galaxy, relics from an early era when the Milky Way was still gathering itself. These stars move on elongated, tilted orbits, unconcerned with the flat rotation of the disk, passing through it at angles, spending most of their time far above or below the plane. Surrounding both disk and halo is an even larger dark matter halo, invisible but massive, shaping the motions of everything within. The visible galaxy is nested inside this unseen structure, like frost outlining a much larger form. The Milky Way is also not alone. It is surrounded by dozens of smaller satellite galaxies, many of which are slowly being drawn inward. Some have already been torn apart, their stars stretched into long, faint streams that wrap around the galaxy like ribbons. These stellar streams are not decorative features. They're records of past encounters, evidence that the Milky Way has grown by absorbing smaller systems over billions of years. Each stream marks the path of a galaxy that once existed independently, now dissolved into the larger whole. These remnants do not disappear instantly. They persist as coherent structures for immense periods, gradually dispersing as their stars mix with the surrounding population. By studying their shapes and motions, astronomers can reconstruct the sequence of mergers that built the galaxy we inhabit. The galactic center itself adds another layer. Dense, energetic and complex, it hosts a supermassive black hole surrounded by tightly packed stars, gas clouds, and energetic processes unlike anything found in the quieter outskirts. Yet even this central region is not separate from the rest. It formed alongside the galaxy, growing as mass flowed inward, shaped by the same slow accumulation that defines everything on cosmic scales. The Milky Way's spiral arms are not rigid structures either. They are patterns, regions where stars and gas bunch up temporarily as material moves through the disk. Stars enter and leave these arms over time, like cars moving through a slow traffic wave. The arms persist not because the same stars stay in place, but because the conditions that create them continue. This means that the galaxy is constantly rearranging itself without ever losing its identity. Layers overlap, structures drift, histories coexist. Even the stars near the Sun belong to multiple populations at once, part of the disk by motion, part of older generations by composition, carrying chemical signatures of stars that lived and died long before the Sun formed. To look at the Milky Way as a single thing is to miss its depth. It is not an island floating intact through space, but an archive of interactions, a system built by slow addition rather than sudden creation. Its shape reflects, not a moment, but a process, one that is still ongoing. New stars form, old stars drift outward, small galaxies approach and dissolve, streams lengthen and fade. The galaxy remains recognizable not because it is static, but because change happens gradually, layered on top of what came before. The Milky Way is a history written in motion, held together by gravity, composed of parts that remember where they came from, even as they become something larger. Beyond the familiar outline of the Milky Way, another large galaxy is already on a slow, deliberate path toward us, not rushing, not accelerating dramatically, simply continuing a motion that began long before there were eyes to notice it. The Andromeda Galaxy, our nearest large galactic neighbour, is currently about 2.5 million light-years away, a distance so vast that light itself takes millions of years to cross it. Yet even across that scale, gravity has been quietly at work. Measurements show that Andromeda is moving toward the Milky Way at roughly 100 kilometers per second, a speed that sounds impressive until it is placed in context. At that rate, it will take more than 4 billion years for the two galaxies to fully merge. This is not a collision in the sense we usually imagine, not an impact or a crash, but a long drawn-out process of mutual rearrangement. Even now, long before their bright disks come anywhere near each other, the extended halos of dark matter surrounding both galaxies already overlap. These halos are enormous, far larger than the visible stars, and they began interacting hundreds of millions of years ago. The galaxies have been influencing each other quietly, exchanging gravitational information without any visible sign. As Andromeda approaches, its path is not perfectly straight. It will swing past, slow, and begin a gradual dance, looping around the Milky Way under the influence of shared gravity. Over time, the two galaxies will pass through each other multiple times, their stars moving mostly unharmed through vast empty spaces. Despite the word collision, individual stars almost never collide. The distances between them are simply too great. Instead, the disks will stretch, distort, and form long tidal tails, streams of stars pulled outward by changing gravitational forces. These structures will persist for hundreds of millions of years, slowly dissolving back into the growing combined system. Gas clouds, more likely to interact, will compress and trigger waves of new star formation, briefly lighting regions of the merging galaxies with fresh activity. Even this increase in brightness will be modest by cosmic standards, spread out over time, part of a gradual transition rather than a sudden transformation. As the merger continues, the original spiral structures will fade, replaced by a more rounded elliptical shape as stellar orbits become randomized. This outcome is common in the universe. Many large galaxies show evidence of similar past mergers, their smooth shapes reflecting histories of slow combination rather than isolated evolution. The Milky Way itself has already absorbed smaller galaxies, and Andromeda has done the same. Their future union is simply the next step in an ongoing process. Throughout all of this, the timescales remain immense. Entire planetary systems will complete billions of orbits around their stars while the galaxies drift closer. Life may arise, flourish, and disappear many times over before the final merger settles. From within either galaxy, the changes will be subtle at first. The night sky will slowly gain a faint growing smudge where Andromeda appears, becoming brighter and larger over hundreds of millions of years. Constellations will shift as tidal forces alter stellar paths. Eventually, the sky will be filled with streams of stars and glowing clouds, but even then the process will feel gradual rather than overwhelming. Gravity ensures that energy is redistributed gently. Orbits adjust, paths curve, systems find new balances. When the merger is complete, the result will not be destruction, but integration. The combined galaxy, sometimes called Milkomeda in speculation, will be larger and more massive, surrounded by an even more extensive halo of dark matter. Its stars will settle into new orbits, its gas will slowly cool and form new generations of stars, and the long history of both galaxies will be preserved in the motions and compositions of their contents. The approach of Andromeda is a reminder that even large-scale encounters unfold according to the universe's preference for patience. Change does not arrive all at once. It accumulates, stretches, and resolves itself over billions of years. Even events described as inevitable are allowed to take their time, becoming part of the same calm rhythm that governs everything else. As carefully as the universe follows its long-established patterns, there are places where those patterns appear slightly bent, not broken, just quietly incomplete, areas where observation has outpaced explanation and where certainty gives way to patience. One of the most well-known examples lies in the oldest light that fills all of space, the cosmic microwave background, the faint afterglow from the time when the universe first became transparent. When scientists mapped this radiation in detail, they found it remarkably uniform, almost the same temperature in every direction, differing by only tiny fractions of a degree. This smoothness tells a story of an early universe that was balanced and calm, expanding evenly. But within that smoothness there is a region that stands out, a patch of sky colder than expected, larger than predicted by standard models. This feature, often called the cold spot, spans an area of sky so wide that it covers a region hundreds of millions of light years across when projected back into space. It is not dramatically colder, only a subtle difference, yet its size and depth are unusual enough that it resists simple explanation. Some researchers suggest it may be the imprint of an enormous cosmic void, a region with less matter than average, stretching across vast distances and affecting the way light passes through it. Others have proposed more speculative ideas, including traces of physics from before. Inflation settled the universe into its current shape. None of these possibilities are confirmed, and the cold spot remains what it has always been, a gentle inconsistency that does not disrupt the overall picture, only reminds us that the picture is still being refined. Nearby in concept, though very different in scale, are galaxies that appear to contain little or no dark matter. For decades, dark matter has been understood as the quiet framework holding galaxies together, explaining why stars in their outer regions move faster than visible mass alone would allow. Yet in recent years, astronomers have identified a small number of galaxies whose stars behave as if dark matter is largely absent. Their motions can be explained almost entirely by the gravity of their visible stars. These galaxies are faint, diffuse, and often located near larger companions, suggesting that interactions may have stripped away their dark matter halos over time. Still, the exact process remains uncertain. They do not invalidate the existence of dark matter, which is supported by overwhelming evidence across the universe, but they complicate the idea that dark matter always behaves in the same way everywhere. They show that cosmic structures can have unusual histories, shaped by environments and interactions that leave subtle but lasting effects. There are other quiet puzzles as well, such as measurements of how fast the universe is expanding. Different methods yield slightly different answers, a discrepancy known as the Hubble tension. Observations of the early universe using the cosmic microwave background suggest one rate of expansion, while measurements based on nearby supernova and galaxies suggest a slightly faster one. The difference is small, only a few percent, but persistent. It has survived improved instruments and refined analyses. Some scientists suspect unknown systematic errors. Others consider the possibility of new physics, perhaps changes in dark energy or additional components in the early universe. For now, the tension remains unresolved, not alarming, not urgent, simply open. This is how many cosmic mysteries exist, not as dramatic gaps, but as gentle mismatches, places where understanding is incomplete, but steadily improving. Even the larger structures in the universe present questions of this kind. Vast arrangements of galaxies sometimes appear larger than expected under assumptions of uniformity, stretching across distances that challenge statistical expectations. Whether these are true, structures, or coincidences of alignment is still debated. Over time, as surveys grow and data accumulates, some mysteries resolve themselves naturally, fading into the background as understanding deepens, while others persist, inviting careful thought rather than quick answers. What unites all of these features is not confusion, but calm. The universe does not demand that it be fully understood at once. It allows questions to remain open across decades, even centuries. Models are adjusted, refined, sometimes replaced, but the underlying behavior of the cosmos continues unaffected. Stars still burn, galaxies still drift, space still expands. The presence of unanswered questions does not destabilize the system. Instead, it reflects the scale of what is being studied. When dealing with a universe billions of years old and trillions of kilometers across, it is natural that some details take time to settle into place. These unexpected features are not flaws in the universe, but reminders of perspective. They show that knowledge grows gradually, just like structure itself, through observation layered upon observation, insight built slowly over time. In that sense, mystery is not a sign of failure, but a natural state within a reality so vast that understanding can never arrive all at once. For a long time after the universe began expanding, there was no light in the way we understand it now. No stars, no galaxies, no glowing points to separate one region from another. Only a vast, cooling darkness filled with simple atoms drifting through space. This period is sometimes called the Cosmic Dark Ages, not because anything dramatic was happening, but because very little was visible. Hydrogen and helium atoms moved slowly under gravity, gathering in faint concentrations that would take hundreds of millions of years to become something more. The universe at this stage was already enormous, already structured by gravity and dark matter, yet visually almost empty. Density differences were small, temperature differences smaller still, and nothing burned brightly enough to illuminate the growing scaffolding beneath. Over time, the quiet pull of gravity began to matter. Dark matter, already arranged into filaments and knots, guided ordinary matter into denser regions, gas clouds, thickened almost imperceptibly, growing cooler as they radiated energy away, becoming more compact over spans of time that dwarf human history. Eventually, in a few rare places, these clouds became dense enough for pressure and temperature to rise rather than fall. When that threshold was crossed, something new happened. The first stars ignited. These earliest stars were unlike most of the stars that exist today. Formed from pristine gas containing almost no heavy elements, they grew massive, some hundreds of times the mass of the Sun. Without metals to help them cool efficiently, they collapsed into large hot objects that burned their fuel quickly. Their light was intense, blue-white and powerful, but they were few and far between. Each one existed in isolation, lighting up a small region of the universe surrounded by darkness. This was not a sudden dawn. Light did not sweep across space in a single moment. Instead, small islands of illumination appeared, separated by immense distances, slowly increasing in number as more stars formed. The radiation from these early stars began to change their surroundings. Their energetic light stripped electrons from nearby hydrogen atoms, turning neutral gas into ionized plasma once again. This process, called reionization, unfolded gradually over hundreds of millions of years. Pockets of ionized gas expanded outward from each luminous source, overlapping slowly as new stars and early galaxies formed. There was no sharp boundary between darkness and light, only a slow increase in transparency as more regions became ionized. As the first stars lived out their brief lives, they ended in powerful explosions, enriching their surroundings with heavier elements forged in their cores. Carbon, oxygen, nitrogen, and other building blocks of later chemistry were scattered into space, mixing with untouched gas. This chemical enrichment changed everything that followed. Gas clouds containing even trace amounts of heavy elements could cool more efficiently, fragmenting into smaller clumps and forming stars of more moderate mass. This marked the transition from the first generation of stars to subsequent ones, stars that lived longer, burned more steadily, and gathered into the first recognizable galaxies. Light became more common, but still not overwhelming. Early galaxies were small and irregular, collections of stars embedded in gas and dark matter, their glow faint and uneven. The universe remained mostly dark by volume, but it was no longer empty of illumination. Over time, as more galaxies formed and merged, their combined radiation completed the process of reionization, leaving the universe largely transparent to light. Photons could now travel vast distances without being scattered, carrying information across billions of light years. This transparency allowed structure to become visible, enabling the universe to look the way it does today, filled with stars, galaxies, and the slow movement of light across space. What is striking about this entire period is not its violence, though explosions occurred, but its pace. Hundreds of millions of years passed between the formation of the first stars and the completion of ionization. Even the appearance of light was a drawn-out process, layered and uneven. Darkness did not vanish. It retreated gradually, giving way step by step. The first light did not erase what came before it. Instead, it built upon it, shaping the universe gently, one region at a time. The glow that fills the cosmos today carries the memory of that slow beginning, a reminder that illumination itself had to grow into place. Measured against the full lifespan of the universe, the present moment occupies a surprisingly early position, closer to the opening chapters than to any kind of conclusion. The universe is about 13.8 billion years old, a number that sounds immense until it is placed beside the timescales that lie ahead. Stars are still forming in large numbers, galaxies are still evolving, and energy gradients remain strong enough to support structure and motion. This era, filled with light and activity, is not the default state of the cosmos, but a temporary phase, one that will eventually give way to quieter conditions. Star formation across the universe has already begun to slow. It peaked several billion years ago when galaxies were rich in cold gas and collisions were more frequent. Since then, much of that gas has been locked away inside stars or heated beyond the point where it can collapse easily. New stars continue to form, especially in spiral galaxies like the Milky Way, but the overall rate is lower than it once was and will continue to decline. This change is not abrupt. It unfolds gently, stretched across tens of billions of years, with long periods where the difference is barely noticeable from one epoch to the next. As star formation slows, the stellar population shifts. Massive, short-lived stars become rarer, while smaller stars dominate. Red dwarfs, the most common type of star, burn their fuel extremely slowly. Some will shine steadily for trillions of years, far longer than the universe has existed so far. Many of these stars have only just begun their lives. Around them, planetary systems may remain stable for unimaginably long spans of time, orbiting stars that change very little over durations that dwarf the entire history of life on Earth. Even as star birth declines, light will not vanish quickly. The universe contains an enormous reservoir of long-lived stars that will continue to glow far into the future. Alongside them are stellar remnants, white, dwarfs, neutron stars and black holes, objects that no longer produce energy through fusion but still play a role in the cosmic story. White dwarfs, the cooling cores of dead stars, radiate their stored heat slowly, taking trillions of years to fade into darkness. Neutron stars remain compact and stable, their internal structures unchanged over vast periods. Black holes, though seemingly eternal, also change, accreting matter at first, then eventually losing mass through faint quantum processes over timescales so long they defy intuitive grasp. As the universe expands, it also cools. Energy becomes more spread out, and differences in temperature grow smaller. This does not mean the universe is heading toward a dramatic ending, but toward a gradual evening out. Over unimaginably long durations, the contrast between hot and cold, dense and empty, will soften. Processes that rely on strong gradients, like star formation and large-scale structure growth, will slow further and eventually cease. Yet even this future state, sometimes called heat death, is not an event but a condition approached asymptotically, never fully reached in any finite time. What is striking is how much remains ahead. The era of stars alone will last far longer than everything that has happened so far. The universe will spend the majority of its existence in conditions that have not yet begun, dominated by faint light, slow cooling, and long-lived remnants drifting through ever-expanding space. From that perspective, the present is not late, not rushed, not on the verge of ending, but early. We're living in a brief luminous interval when complexity is possible, when energy flows freely enough to support structure, motion, and change. The future stretches outward for durations so long that even the most ancient events we can observe now will eventually seem recent by comparison. Time does not run out quickly in the universe, it accumulates. The story continues not toward a sudden conclusion, but toward a long, drawn-out quiet, one that takes almost all of eternity to arrive. As the universe continues its long expansion, the future it moves toward is not defined by destruction or collapse, but by a gradual settling into simplicity. Galaxies drift farther apart as space stretches between them, not because they are accelerating through space, but because the space itself keeps growing. Over billions of years, this expansion carries distant galaxies beyond one another's observable reach. Light emitted in those regions will never arrive elsewhere, not because it fails, but because the distance grows faster than it can close. Each galaxy slowly becomes an island, surrounded by darkness not from absence, but from separation. Within those islands, stars continue to shine for immense spans of time, but even this activity slowly winds down. Gas that once formed new stars becomes scarce, either locked away in stellar remnants or dispersed too thinly to collapse again. The skies of distant futures will hold fewer bright points, and the remaining stars will be small, steady, and long-lived, burning quietly without dramatic change. Over time, stellar deaths will outnumber stellar births, and the universe's overall brightness will continue to fade. This fading does not happen all at once. It stretches across trillions of years, allowing structures to persist far longer than any living memory. Eventually, galaxies will be populated mostly by remnants. White dwarfs cooling slowly, neutron stars locked into silent stability, and black holes drifting through increasingly empty space. Even black holes, often imagined as eternal, will not remain unchanged forever. Through faint quantum effects at their horizons, they will lose mass at a rate so slow that the process takes longer than stars ever lived. When the last black holes finally evaporate, the universe will be left with only low-energy particles spread thinly across vast distances. This state is sometimes called heat death, but the name can be misleading. Nothing dies in a moment. No final event marks the transition. Instead, energy differences even out, leaving fewer opportunities for work, motion, or complexity. Temperature approaches uniformity, but never reaches absolute zero. Motion continues, but without structure. Time does not stop. It simply passes in a universe where very little happens. In this future, there is no catastrophe, only quiet. The laws of physics remain the same, but their outcomes become simpler as energy spreads thin. Particles continue to move, fields continue to exist, and space continues to expand. The universe does not disappear. It becomes calm in a way that is difficult to imagine from within an era filled with stars and galaxies. The long cooling of the cosmos is not something to be feared. It is the natural result of processes unfolding exactly as they have since the beginning, without interruption or urgency. the same patience that governed the formation of the first atoms, the ignition of the first stars, and the slow assembly of galaxies continues to shape the future. Everything that exists now will eventually be part of that quiet state, not erased, but transformed, spread thinly across space and time. From the perspective of deep time, this settling is not an ending but a resolution. The universe begins with energy concentrated and ends with energy dispersed, a gentle arc that spans lengths of time so vast that beginnings and endings lose their sharpness. Even this far future does not erase the past. The information carried by particles, the imprints left in space-time, and the structure of physical laws remain as traces of everything that came before. The universe holds its history not as memory, but as consequence, with every state arising naturally from the one before it. In that sense, the future grows quiet not because something goes wrong, but because everything proceeds exactly as it should, after everything that has unfolded, after the long expansion, the slow cooling, the forming and fading of stars, the drifting apart of galaxies, there is one outcome that stands quietly apart from all the others. Matter did not merely rearrange itself into larger or colder structures. In at least one small region of the universe, it organized into something capable of noticing what had happened. The elements that make up living bodies were not present at the beginning. Hydrogen and helium filled the early universe almost alone. Everything heavier had to be made later, inside stars that lived and died over immense spans of time. Carbon, oxygen, nitrogen, calcium, iron, all were forged under pressure and heat, assembled atom by atom in stellar interiors, then released back into space through winds and explosions gentle on cosmic scales. Those atoms drifted for millions of years, sometimes billions, becoming part of new stars, new planets, and eventually complex chemistry. Nothing about this process was directed. There was no plan for awareness, no requirement that matter become reflective, yet complexity built upon complexity simply because conditions allowed it to persist. Stable stars provided long stretches of time, planets formed in steady orbits, chemistry explored countless combinations, most fleeting, some enduring. Eventually, arrangements appeared that could store information, respond to their surroundings, and adapt. Over time, that responsiveness deepened into awareness. In this sense, consciousness is not separate from cosmic history. It is one of its rare but natural outcomes, a continuation of the same slow processes that shaped galaxies and stars. The atoms involved are ordinary, the forces are familiar. What is unusual is not the material, but the pattern. A portion of the universe became capable of reflecting on the universe itself. This does not change the laws of physics or interrupt the universe's long-term direction. Expansion continues. Stars will still fade. Galaxies will still separate. Awareness does not halt any of that. It exists briefly within it, a momentary structure supported by energy flows that will one day dissipate. Yet while it lasts, it allows the universe to be known from the inside. Through observation, memory, and thought, the universe gains perspective on its own history. It can reconstruct events that happened billions of years earlier. It can measure expansion, detect ancient light, infer invisible matter, and trace its own origins back to a time before stars existed. This is not a destiny fulfilled, but a state reached, temporarily, without urgency or permanence. Eventually, as energy spreads thinner and complexity becomes harder to maintain, awareness will fade along with everything else. That too will happen slowly. There will be no moment when the universe notices it has become quiet again. The same patience that governed the beginning will govern the end. In that sense, nothing is lost. The universe does not require remembrance to continue. But for a brief span of cosmic time, it has contained arrangements of matter that could look outward, trace long arcs of cause and effect, and understand that everything they are made of once burned inside stars. The universe did not stop evolving. It evolved into a state where it could reflect briefly on its own vastness before continuing on, unhurried, into the long calm that still lies ahead. Sleep well.